Okay, so for probability and stats, this is from packet 10.5. This is practice C. And if you're trying to find this in your packet, this is on page 14, and it is the 14 in a circle. Quick note, depending on the packet you received, it might be hard to see that 14 in the circle because it kind of got cut off at the bottom. It's towards the bottom left, but I'm confident you'll be able to find this page in your packet. It's also a little out of order for this packet. Practice C in this packet is in between practice A and practice B, but that's a little mistake there. Again, I'm confident you'll be able to find this page. So I'm going to try my best to go over all the questions in this packet. I should have in the description for this video a little timestamp if you want to skip ahead. You should be able to see in the description, like, if you want to skip ahead to problem number 5 or problem number 8 or 9 or something, you should be able to just click on the timestamp in the description so that you don't have to watch the whole thing or try and skip through it on your own. But here we go, starting with problem number 1 on practice C. Our instructions are identify the sample space and the outcome shown for each experiment. So we have rolling a die and spinning the spinner. So remember, there's two parts to this. There's identify the sample space and then also identify the outcome shown. And remember, outcome shown is relatively easy, I think, but I won't ask you for the outcome on the test. I will simply ask you for the sample space. So if we want to define for ourselves sample space, remind ourselves what that is. Sample space is simply a list of all the possible outcomes. What could happen in this situation? Okay, so that's all we're going to do. We're gonna say what could happen. Now this is what we call a compound event. We are doing two things together. We are rolling a die and we are spinning a spinner, and we want to combine the two outcomes from the die and the spinner as one outcome. So what I'm going to do here is I'm going to do a tree diagram, or rather, a partial tree diagram, and I'm going to start with the spinner. Okay, so that's the first thing I'm going to do. So the spinner, what could happen on the spinner that I'm showing here? I have 4 possible outcomes. So I spin the spinner. It could be that I get A, it could be that I get B, it could be that I get C, or I could get D. So for the spinner itself, I have 4 possible outcomes. Now, if I'm going to continue my tree diagram is great for these compound events when you do more than one experiment combined, a spinner and a die, or flipping a coin multiple times. So rolling the die, then, just for that by itself, there's 6 possible outcomes. But if you remember your tree diagram, you would do 6 branches off of A, you would do 6 branches off of B, you would do 6 off of C, I think that's only 5, there's 6, and then you would do 6 off of D. Now that's going to be kind of cramped to write everything there, but the idea that I'll list here is that we could get A on the spinner. And if we get A on the spinner, what could happen on the die? Well, we could get a 1 on the die. Or if we get A on the spinner, we could get a 2 on the die. Or we could get A on the spinner and a 3. Or A and a 4. Or A and a 5. Or A and a 6. So that's if we get A. If we follow this branch, these are all the outcomes getting A on the spinner. The 6 possible outcomes on the die if we get A on the spinner. But what if it wasn't A on the spinner? We'll switch colors here. What if it was B? What if we got B on the spinner? Well, we could get B and then a 1 on the die, B on the spinner and then 2 on the die, B on the spinner, then 3, B and then 4, B and then 5, B and then 6. And that's it. That's all that can happen if we get B on the spinner. But what if we didn't get B on the spinner? What if we got C on the spinner? Well, we could get a C and a 1, C and a 2, C3, C4, C5, and C6. But what if we didn't get C on the spinner? What if we got D instead? Well, we can get D on the spinner and we can get 1 on the die, D and 2, D3, D4, D3, D4, D5, and D6. Now that's all of it. Now this is a long list, but this is our sample space. for this experiment that combines two things, rolling the die and spinning the spinner. As far as the outcome shown, which outcome is shown? Well, we have C on the spinner and a 2 on the die, so that's this one right here. The outcome shown is C on the spinner, 2 on the die. So again, on the test I won't say what outcome is shown, I'll just ask you for the sample space on the test. But that's it. If you want to count those up, we have 24 different possibilities, and that corresponds to the 4 possibilities for the spinner times the 6 possibilities for the die. That's something we'll get into later. It's called a counting technique, the fundamental counting principle. But for now, we've got our answer for number 1. Here's the sample space, A with any of the numbers, B with any of the numbers, C with any of the numbers, D with any of the numbers, and then the outcome shown, C with a 2. So there's number 1. Here for number 2 is same thing as number 1. We're identifying the sample space and the outcome shown. Tossing 3 coins. This will be a little bit nicer to do a complete full tree diagram than number 1 was. So we'd have the first coin. If I break it up individually, first coin has 2 options. It could be heads or it could be tails. Okay. And then the second coin, if you remember, the second coin I'm going to take into consideration what happened on the first coin. So if the first coin was heads, then it could be heads or tails on the second coin. But if the first coin was tails, then I'm down here, and the second coin could be heads or tails. And again, it's the second coin is not affected by the first coin. Either way, whether it's heads or tails first, the second coin could be heads or tails. These are called independent events, and that's another thing we'll talk about later on. But still, it's going to help me keep track of everything here. And now the third coin, I want to follow each of these branches. There we go, third coin. So if it's heads on the first coin and heads on the second coin, well, then the third coin could be heads or tails. If it's heads on the first coin, tails on the second coin, the third coin could still be heads or tails. Every one of these endpoints I have from the second coin, I'm going to branch off 2 more branches with another heads and tails. So each of these represents an endpoint for the entire experiment of flipping 3 coins. So now that's all. Now that is all that is left for me to do is write down the results here. So the results, what could have happened? Well, if I end right here, this was heads on the third coin, heads on the second coin, heads on the first, or going the other way, heads, heads, heads. If I end up right here, that would be heads, heads, tails. I remember some of you might be able to come up with this list without doing the tree diagram. That's fine. Again, I think the tree diagram, I would have you practice it. I would want you to be able to do it because I think it's great when we start assigning probabilities, when we start putting numbers to these, like, oh, it's a 1 out of 2 chance or 50% or something like that. It's going to be helpful potentially. So if I'm here, it was heads, then tails, then heads. Right here would be heads, then tails, then tails. Here, if I wind up right here, whoop, what are we doing? What's happening? Having some technical difficulties right now. Let's try this again. There we go. Tails, then heads, then heads. Oh boy. My pen is not working here, so I'll have to use the mouse. Tails, then heads, then heads. If I wind up here, tails, heads, tails. If I wind up right here, this is tails, tails, heads. And if I wind up at the bottom, this is tails, tails, tails. Tails on all 3 coins. So this right here is the sample space. That's my sample space. It's all the possible outcomes, all the possible results that we have there. So you can count them up. That's, remember, we're combining these. I know it's 3 coins, but we're combining all 3 coins. So this is one outcome. Heads, 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 that's one outcome for this experiment. Heads, heads, tails is one outcome, etc. There's 8 outcomes there, if you count them up. And that corresponds to 2 possibilities for the first coin times 2 possibilities for the second times 2 possibilities for the third. 2 times 2 times 2 would give you 8. Again, you don't have to worry too much about that right now, but that is something we will look at later on before our final test here. Now the only other thing for me to do on number 2 is to identify the outcome shown. Well, the outcome shown is heads on all 3 coins. So the outcome would be heads, heads, heads. That's the one outcome that we have there out of 8. So there we go. So there's number 1 and number 2. Both of those are a little tricky because they are what we call compound events. It wasn't just flipping a coin once or flipping one coin or just spinning a spinner or just rolling a die. It was combinations of those things. But again, hopefully this idea of a tree diagram can help you. But otherwise we'll move on. Okay, so moving on here to 3 through 5 on our practice C. Our instructions are to describe the likelihood of each event. Now, they don't tell us here, but if you flip back to like practice A, or let's see, it's practice B also has it, but we're going to use one of 5 terms or phrases, and I have them down at the bottom, so it's impossible, unlikely, as likely as not, likely, or certain. It's multiple choice here. It's one of these 5. And if you just remember here, impossible means that there is a 0% chance of happening. It's not going to happen. Unlikely means it's less than 50%, but more than 0. It could happen, just probably not. As likely as not means it's a 50% chance. It's equally likely to happen as to not happen. Likely means you're more than 50%, but less than 100%. It will probably happen, but not guaranteed, not certain. And then certain means 100%, means guaranteed, means it will happen. So for each of these events, of each of these descriptions, we want to use one of these 5 terms to describe it. So if we start here with number 3, Doug has already flipped a coin 9 times and it lands heads each time. Doug flips a coin the 10th time and it lands heads. Now here, I think we would want to consider perhaps, something we haven't yet got into. Number 3, are we talking about experimental? Are we going off of the experimental results? Or are we going off of the theoretical, what we would expect? You could make the case, and I think actually one of your worksheets that I gave you, I gave you something similar with, I think it's coins, or excuse me, not coins, marbles, and it looks at the experimental probability, or maybe it's rolling a die, I forget. But it's something about, we use the results of the experiment to use these terms. So if I use Doug's experiment, he flipped a coin 9 times and it lands heads each time. If I go with experimental, number 3, Doug flips a coin the 10th time and it lands heads. That would be certain. If I base it off of the experiment, I go, every time Doug has flipped it, it's landed heads. So he's going to do it one more time, and how would I describe that it's going to land heads? I go, it's going to be certain based off of the experiment. However, I don't think probably that they want us to talk about the experimental results when we describe this event. I think, I think they probably want us to talk about theoretically describe the likelihood that on the 10th time it lands heads. And this is one thing where there's a phrase, and I'll type this out here, that the coin has no memory. So some people think, and this is where, this is what's sometimes known as the gambler's fallacy, that you might think, oh, tails is due. Tails has to come up because it can't keep coming up heads. It's got to eventually come up tails. That's something known as the gambler's fallacy, or a version of it. But the coin has no memory. The coin doesn't remember what happened in the last 9 flips. So this would actually be theoretically, which is what I'm going to go with for my final answer here, theoretically this would be as likely as not. Heads and tails, and whoops, let me write that, see if I can write that a little bit better, as likely as not. Heads and tails are equally likely. There's one side that's heads, one side that's tails. So we're going to reject this idea that it's certain, Basing it off of the experiment, yes, it would be certain. Maybe it's a trick coin. Maybe it's a coin that only has heads. Both sides are heads. Maybe we just don't know it. But I'm assuming this is what we call a fair coin. So for any given flip, to get heads, it's as likely as not compared to getting tails. Okay, so moving on, number 4. Number 4 is a little bit of a tricky one if you forget about what prime numbers are. But number 4 says, Shannon rolls a 17 on a number cube that shows the first 6 prime numbers. So you might need a reminder as to what prime numbers are. And here I've written out the first 6 prime numbers. Prime numbers, you won't need to know this on the test. I'll make sure that the test is fairly simple here. But if you want to remind yourself what prime numbers are numbers that can only be divided nicely by themselves and 1. No fractions or decimals are allowed when we do this division, no remainders. So 2 is the first prime number. 1 technically doesn't count as a prime number, even though it might fit the description, but 1 is not counted as a prime number. So you've got 2 is a prime number, 3 is a prime number, 4 is not because it can be divided by 2, 5 is, 6 is not because 6 can be divided by 2 or 3, 7 is a prime number, 8 is not because it can be divided by 2 or 4, 9 is not because it can be divided by 3, 10 is not because it can be divided by 2 and 5, 11 is, 12 is not, 12 has a lot of divisors, 2, 3, 4, 6, 13 is another prime number. So we want to roll a 17 on a number cube that shows these 6 numbers. So I look at that and I go, this would be my sample space. There is no 17 in the sample space, which means 17 cannot happen. Alright, so for this one, which of these words do we want to use here? This would be impossible. If you've got the first 6 prime numbers, 17 is not amongst the first 6 prime numbers. Impossible, okay? And let me make that B a little bit better. It would be impossible there. If we included 7, 17 would be the 7th prime number. So if we included the first 7 prime numbers, then 17 would have a chance. It would still be unlikely, but it would have a chance. Okay. So again, on the test, you won't have to worry about what are prime numbers, but you'll still want to know, like, okay, if I give you this sample space, if I told you you're going to pick a number, randomly pick a number from this set of numbers, 2, 3, 5, 7, 11, 13, describe the likelihood that you get a 17. You would say, there is no 17, that is impossible. Not going to happen. 0% chance. Okay, so last one in this section now, number 5, we're supposed to describe the likelihood that 3 people in a class of 20 have the same birthday. Now, again, choosing from impossible, unlikely, as not likely, or certain, it's certainly not impossible. It could happen. It's not certain to happen, so it's either unlikely as not, or likely. It could happen, but it doesn't have to happen. Most people right away would probably say, oh, that's going to be unlikely. That's probably not going to happen. But this is actually a tricky problem. If you remember, I think in class I showed you last week the book. The title is Coincidences, Chaos, and All That Math Jazz. And that's in the classroom. It's on one of the bookshelves in the back, and you're welcome to take a look at it. But they actually describe, if I remember correctly, they say if you have 45 people in a group, they approximate that it's about a 95% chance that 2 people have the same birthday. And they take you through the math on that. Whoops, I erased all that. But 45 people, there's like a 95% chance that at least 2 people have the same birthday, and that's kind of surprising. It's almost certain, not certain, but almost certain, that if you had 45 people, you'd have 2 people with the same birthday. Now, this is different though. This is 3 people, so that's more, and it's only a class of 20, so it's a smaller group. You do have to be careful on this. We can calculate this, although it's kind of a tough calculation. If my calculation is correct, for number 5, I calculate that there's approximately a 59% chance that no 2 people have the same birthday. That's my calculation. Now, it's very possible that I'm making a mistake on that. Let's see if I can scoot this somewhere where we can see it better. It's very possible I'm making a mistake on that, but that's just 2 people, and we're saying it's a 59% chance that 2 people do not have the same birthday. So that would put us, certainly, as you probably suspected from the very beginning, that this is unlikely to happen. Okay. But again, if you're interested, check out this book, Coincidences, Chaos, and All That Math Jazz, because it's actually surprising sometimes, the chances that 2 people or more people would have the same birthday. Alright, so continue here, practice C in our packet 10-5 with 6, 7, and 8. The first thing we're doing, if we read the instructions here, an experiment consists of spinning a spinner and tossing a coin. Use the results in the table to find the experimental probability of each event. So this is kind of similar to number 1, where we were spinning a spinner and rolling a die, but now the spinner has apparently red, blue, and yellow, and then we're not rolling a die, but we're flipping a coin. But they've given us the outcomes in the experiment. We're supposed to find the experimental probability. So down here I've written to remind you the definition that this packet gives for experimental probability. And this is on page 3 in a circle in your packet. It says experimental probability equals, remember this is a big fraction bar, it's a fraction of the number of times the event occurs, whatever event we're finding the probability of, over the total number of trials. So all we have to do here, one thing I think I mentioned is anytime you have a table like this with frequency, what's called a frequency table, if you're not given the total, I would figure it out, because most questions the total will come up. So if we add up all these frequencies, 3 plus 5 is 8, and 4 and 4 is another 8, that's 16, 7 and 2 is 9, so that puts us at a total of 25, if I'm counting that correctly. Okay. So as I look for the experimental probability of each of these events, the total number of trials is going to be 25 for all of these. So every fraction, if I want, I can start with over 25. For every single one of these, because every single one is out of 25 trials, 25 total times. So not even looking at the question, I can start with all of these as out of 25. So number 6, the experimental probability of spinning red and tossing tails. Now this is something we've talked about before. When we use the word or, let me put that in quotes, when we use the word or, we would add, and we said either could happen. Either event could happen. If it's pepperoni or sausage, I go, I don't care which one it is, either one could happen. But when we use the word and, this is where it's a little more difficult. Both have to happen. So when we say and tossing tails, spinning red and tossing tails, there's only one place where that happens. They both have to happen. So spinning red and tossing tails is right here. I do not get to count red with heads. I don't get to count that one. I don't get to count tails with blue or tails with yellow. I can only count when it's both red and tails. So that happened 4 times. That would be 4 out of 25 for my experimental probability. And that's it for number 6. Okay, so looking here at the next problem, we're spinning blue and tossing heads or tails. So this one's a little tricky because they're throwing both of these words at us here. We have spinning blue and tossing heads or tails. So we want blue, but it could be blue and heads, or it could be blue and tails. So either one of those outcomes, it has to be blue, but then heads or tails, I don't care if it's heads or tails. Either one could happen, heads or tails, but it has to be blue. So we have 5 here for blue and heads, 7 here for blue and tails, could be either one, and we said we're going to add those together. So 5 plus 7 would give us 12. And then our experimental probability, 12 out of 25, still a total of 25. So that's what we have there. Okay. And then for our last one here, not tossing heads. Not tossing heads, so that means Any place where we toss heads is out. So red and heads, that's out. Blue and heads, that's out. Yellow and heads, that's out, because I want not heads. So red and tails, hey, that's in because it's not heads. Blue and tails, that's in because it's not heads. Yellow and tails, that's in because it's not heads. So it could be any of these three. So what we'll do is we'll add these up. 4, 7, and 2. I believe when we add that together, we have 13 times it happened out of 25 total. So keep that in mind when we say it could be this one or this one or this one, we're going to add those numbers together. If we said it had to be something and something else, both of them have to happen. But in this case, for this experiment, it's always out of 25 because that's our total number of trials. Alright, so number 9 on our Practice C page says a computer repair person tried to shut down a program 80 times and found it closed properly 55 times. Part A asks, what is the experimental probability that the program will close properly? So experimental probability, again, I'm looking down here at this definition. Okay, same definition we used in 6 through 8. So we want the number of times the event occurs. The event is closing properly. Okay, how many times did it close properly? Well, it closed properly 55 times, so that is my numerator. Okay. Now, the number of trials, and remember, a trial is trying it out, performing an experiment. In this case, the experiment is shutting down the program. So we did that 80 times, so that would be our denominator. Okay. And as far as I'm concerned, you can leave your answer as that fraction. I'm just taking a look here. They do give it as a decimal, or excuse me, as a percent. And if you want, this is okay. This is great for a final answer as far as I'm concerned. But then you might be like, well, okay, so was it likely to happen? Unlikely? As likely as not? What? So if you want to remind yourself on how to get the percentage, you would say this would be your fraction right here. And then to get your percentage, you could, again, one way to do this, set this equal to some percentage that we'll figure out, call it x. Percentage is out of 100 though. And then you can do cross multiplication and division. 55 times 100 divided by 80, and that would give you your percentage. And looks like what they have as the answer is 68.75. But again, I'm okay if you leave it as the fraction. Part B on number 9 asks us, it says, an analyst closes the program 32 times. Predict the number of times the program will close properly. So the thing to notice here, we're still talking about closing properly, and that's what we talked about. We had an experimental probability of closing properly, so we're still talking about the same thing. So we can here look at, in the experiment, we had 55 times it closed properly out of 80 times. And now, let's see here, our prediction here, we don't know how many times it'll close properly. That's what we're going to guess, but it's going to be out of 32 times total. We're going to close the program 32 times. So just like here it was shut down or close the program 80 times, that was our total here. Now we're going to try it 32 times, and we're going to see what's going to happen here. So these fractions, we can set them equal to each other, and now we can do our cross multiplication and division. So we can take our 55 times 32 and divide by 80. 55 times 32 divided by 80. Now this is, let's see, we'll just see what the calculator gives us here. Here's my calculator, so I'm going to do 55 times 32 and divide by 80, and they say 22 exactly. I was wondering if we were going to have to round. So it gives us 22, so that's our prediction. Again, we might be wrong on that. We might try that out. 22 times is what we predict. It might be more or less than 22, but based on our experiment, that's what we would predict. If our 32 trials here matches our experiment, 22 times would be our prediction. Okay, and the last problem here on practice C, number 10, says a teacher tested 80 calculators and found 5 not working. What is the experimental probability that a calculator does not work? And again, we want to be careful here. We have does not work. Does not work. Okay, so we had 5 that were not working. So just in case, because sometimes they'll get sneaky, they'll get tricky, and they'll say, what's the experimental probability that it does work? And then we have to think critically and read carefully there. But we're talking about not working, that's our 5. So again, down at the bottom here, this basic definition of experimental probability that is oh so important. The experimental probability is the number of times the event occurs. How many times did the calculator not work? That was 5 times. So we have 5 times as our numerator, and then the total number of trials. How many times did we try to turn on a calculator or test the calculator? And that would be the 80. Tested 80 calculators. That's our number of trials. So there is our probability as a fraction, and again, for me, I'm fine if you want to stop there. Again, I think the answer probably has it as a percent, and that's where if you want this as a percent, you would set this equal to your percentage over 100, and then do your cross multiplying and dividing, and you can get the answer there. But otherwise, for me, I'm okay with 5 over 80 as your probability. And then part B, to finish up here, the classroom has 32 calculators. Predict the number of calculators that will not work. So we're still talking about not working, just to be clear on that. So for my experiment that the teacher performed, we had 5 that did not work out of 80 total. And for our prediction, we're looking at how many will work out of 32 total. So we can set these fractions equal to each other, and then we can cross multiply and divide 5 times 32 and divide by 80. So 5 times 32 divide by 80, and we'll see if we get a nice whole number this time. 5 times 32 divided by 80, yep, that's going to be 2, exactly 2. So again, didn't have to worry about rounding there, but that would be our prediction. 2 calculators we would guess, based on the experiment, 2 calculators that will not work. And there's our final answer. All right. So I hope this helped you out. If you haven't yet finished practice A or practice B, I would recommend go back, try those out. I believe typically practice A and B are usually easier than practice C, so hopefully with this guidance that you would then be able to do A and B without too much difficulty.